Hello friends, here we meet again with a new topic of discussion, that is energy and energy transfer. Whether we realize it or not, energy is an important part of most aspects of daily life. The quality of life and even its sustenance depends on the availability of energy. Therefore, it is important to have a good understanding of the source of energy, the conversion of energy from one form to another, and the consequences of these conversions. Energy exists in numerous forms such as thermal, mechanical, electrical, chemical, and nuclear. Even mass can be considered a form of energy. Energy can be transferred to or from a closed system in two distinct forms, heat and work. For control volumes, energy can also be transferred by mass flow. An energy transfer to or from a closed system is heat if it is caused by a temperature difference. Otherwise, it is work and it is caused by a force acting through a distance. In this lecture, we shall be looking at the concept of energy and define its various forms, discuss the nature of internal energy, discuss thermal, linear, and volume expansions. Concept of energy. We are familiar with the conservation of energy principle, which is an expression of the first law of thermodynamics back from our high school years. We are told repeatedly that energy cannot be created or destroyed during a process. It can only change from one form to another. This seems simple enough, but let's test ourselves to see how well we understand and truly believe in this principle. Consider a room whose door and windows are tightly closed and whose walls are well insulated so that heat loss or gain through the walls is negligible. Now let's place a refrigerator in the middle of the room with its door open and plug it into a wall outlet. You may even use a small fan to circulate the air in order to maintain temperature uniformity in the room. Now, what do you think will happen to the average temperature of air in the room? Will it be increasing or decreasing, or will it remain constant? Probably the first thought that comes to mind is that the average air temperature in the room will decrease as the warmer room air mixes with the air cooled by the refrigerator. Some may draw our attention to the heat generated by the motor of the refrigerator and may argue that the average air temperature may rise if this heating effect is greater than the cooling effect. But they will get confused if it is stated that the motor is made of superconducting materials and thus there is hardly any heat generation in the motor. Heated discussions may continue with no end in sight until we remember the conservation of energy principle. If we take the entire room, including the air and the refrigerator, as the system, the only energy interaction involved is the electrical energy crossing the system boundary and entering the room. The conservation of energy requires the energy content of the room to increase by an amount equal to the amount of the electrical energy drawn by the refrigerator. The refrigerator or its motor does not store this energy. Therefore, this energy must now be in the room air and it will manifest itself as a rise in the air temperature. Therefore, we found that energy is conserved during the process of operating the refrigerator placed in a room. The electrical energy is converted into an equivalent amount of thermal energy stored in the room air. Forms of energy. Energy can exist in numerous forms such as thermal, mechanical, kinetic, potential, electric, magnetic, chemical and nuclear, as we discussed earlier, and their sum constitutes the total energy of a system. The total energy of a system on a unit mass basis is denoted by E and is expressed as E is equal to E upon m. Here E is the total energy. Thermodynamics provides no information about the absolute value of the total energy. It deals only with the change of the total energy, which is what matters in engineering problems. Thus, the total energy of a system can be assigned a value of 0 at some convenient reference point. The change in total energy of a system is independent of the reference point selected. The decrease in the potential energy of a falling rock, for example, depends on only the elevation difference and not the reference level selected. In thermodynamic analysis, it is only helpful to consider the various forms of energy that make up the total energy of a system in two groups, macroscopic and microscopic. The macroscopic form of energy are those which a system possesses as a whole with respect to some outside reference frame, such as kinetic and potential energies. As shown in this figure, the macroscopic energy of an object changes with velocity and elevation. The microscopic form of energy are those which are related to the molecular structure of a system and the degree of the molecular activity, and they are independent of outside reference frames. The sum of all the microscopic form of energy is called the internal energy of a system. Physical insight to internal energy. Internal energy, as we defined, is the sum of all the microscopic forms of energy of a system. It is related to the molecular structure and the degree of molecular activity and can be viewed as the sum of the kinetic and potential energies of the molecules. To have a better understanding of the internal energy, let us examine a system at the molecular level. The molecules of a gas move through space with some velocity and thus possess some kinetic energy. This is known as the translational energy. The atom of polyatomic molecules rotate about an axis, and the energy associated with this rotation is the rotational kinetic energy. The atoms of a polyatomic molecule may also vibrate about their common center of mass, and the energy associated with this back and forth motion is the vibrational kinetic energy. For gases, the kinetic energy is mostly due to translational and rotational motions, with vibrational motion becoming significant at higher temperatures. The electrons in an atom rotate about the nucleus and thus possess rotational kinetic energy. Electrons also spin about their axis, and the energy associated with this motion is the spin energy. The portion of the internal energy of a system associated with the kinetic energies of the molecules is called the sensible energy. The average velocity and the degree of activity of the molecules are proportional to the temperature of the gas. Therefore, at higher temperatures, the molecules possess higher kinetic energies, and as a result, the system has a higher internal energy. The internal energy is also associated with various binding forces between the molecules of a substance, between the atoms within a molecule, and between the particles within an atom and its nucleus. The forces that bind the molecules to each other are strongest in solids and weakest in gases. If sufficient energy is added to the molecules of a solid or liquid, the molecules overcome these molecular forces and break away, turning the substance into a gas. This is a phase change process. Because of this added energy, a system in the gas phase is at a higher internal energy level than it is in the solid or the liquid phase. The internal energy associated with the phase of a system is called the latent energy. In daily life, we frequently refer to the sensible and latent forms of internal energy as heat, and we talk about heat content of bodies. In thermodynamics, however, we usually refer to those forms of energy as thermal energy to prevent any confusion with heat transfer. Distinction should be made between the macroscopic kinetic energy of an object as a whole and the microscopic kinetic energies of its molecules that constitute the sensible energy of the object. The kinetic energy of an object is an organized form of energy associated with the orderly motion of all molecules in one direction in a straight path or around an axis. In contrast, the kinetic energies of the molecules are completely random and highly disorganized. As we will discuss in later lectures, the organized energy is much more valuable than the disorganized energy, and a major application area of thermodynamics is the conversion of disorganized energy, that is heat, into organized energy, that is work. We will also see that the organized energy can be converted to disorganized energy completely, but only a fraction of disorganized energy can be converted to organized energy by specially built device called heat engines like car engines and power plants. A similar argument can be given for the macroscopic potential energy of an object as a whole and the microscopic potential energies of the molecules. Thermal expansion. You can often loosen a tightened metal jar lid by holding it under a stream of hot water. Both the metal of the lid and the glass of the jar expand as the hot water adds energy to their atoms. However, because the atoms of the metal move farther apart than those in the glass, the lid expands more than the jar and thus is loosened. Such thermal expansion of materials with an increase in temperature must be anticipated in many common situations. When a bridge is subject to large seasonal changes in temperature, for example, sections of the bridge are separated by expansion slots so that the sections have room to expand on hot days without the bridge buckling. When a dental cavity is filled, the filling material must have the same thermal expansion properties as the surrounding tooth. Otherwise, consuming cold ice cream and then hot coffee would be very painful. The thermal expansion properties of some materials can be put to common use. Thermometers and thermostats are based on the differences in expansion between the components of bimetal strip. Figure A shows a bimetal strip consisting of a strip of brass and a strip of steel welded together at temperature T0, and the figure B shows the strip bends at temperature above the reference temperature. Below the reference temperature, the strip bends the other way. Many thermostats operate on this principle, making and breaking an electrical contact as the temperature rises and falls. Also, the familiar liquid in glass thermometers are based on the fact that liquids such as mercury and alcohol expand to different extent than their glass containers. Linear expansion. If the temperature of a metal rod of length L is raised by an amount delta T, its length is found to increase by an amount delta L equal to L alpha delta T. Here alpha is a constant called the coefficient of linear expansion. The coefficient alpha has a unit per degree or per Kelvin and depends on the material. Although alpha varies somewhat with temperature, for most practical purposes it can be taken as constant for a particular material. The thermal expansion of a solid is like photographic enlargement, except that it is in 3 dimensions. Part B of the figure shows the thermal expansion of a steel ruler. Equation delta L is equal to L alpha delta T applies to every linear dimension of the ruler, including its edge, thickness, diagonals, and the diameter of the circle etched on it and the circular hole cut in it. If the disc cut from that hole originally fits comfortably in the hole, it will continue to fit comfortably if it undergoes the same temperature increase as the ruler. Volume expansion. If all dimensions of a solid expand with temperature, the volume of that solid must also expand. For liquids, volume expansion is the only meaningful expansion parameter. If the temperature of a solid or liquid whose volume is V is increased by an amount delta T, the increase in volume is found to be delta V is equal to V beta delta T. Here, beta is the coefficient of volume expansion of the solid or liquid. The coefficients of volume expansion and linear expansion for a solid are related by beta is equal to 3 alpha. The most common liquid, water, does not behave like other liquids. Above about 4 degrees centigrade, water expands as the temperature rises, as we would expect. Between 0 and about 4 degrees centigrade, however, water contracts with increasing temperature. Thus, at about 4 degrees centigrade, the density of water passes through a maximum. At all other temperatures, the density of water is less than this maximum value. This behavior of water is the reason lakes freeze from the top down rather than from the bottom up. As water on the surface is cooled from, say, 10 degrees centigrade towards the freezing point, it becomes denser, or we could say heavier, than lower water and sinks to the bottom. Below 4 degrees centigrade, however, further cooling makes the water then on the surface less dense or lighter than the lower water, so it stays on the surface until it freezes. Thus, the surface freezes while the lower water is still liquid. If the lake froze from the bottom up, the ice so formed would tend not to melt completely during the summer because it would be insulated by the water above. After a few years, many bodies of open water in the temperature zones of Earth would be frozen solid all year round, and aquatic life could not exist. So friends, here we come to the end of our discussion in this lecture, and therefore we sum up. The sum of all forms of energy of a system is called total energy, which consists of internal, kinetic and potential energy for simple compressible systems. Internal energy represents the molecular energy of a system and may exist in sensible, latent, chemical and nuclear forms. All objects change size with change in temperature. So that is it for today. In the next lecture, we shall be discussing heat, energy transfer by heat, and the 3 mechanisms of heat transfer, that is conduction, convection and radiation. Thank you very much.